Hi, Dinesh. I'm not sure we're meeting now, or maybe we are. Wait. Oh, hi, Samar. Okay. Oh, I guess there was 3 of us now. It's already 11 people. I got so confused by the time zones. I'm sorry. So, Samar, so should I ping at channel?
Yeah, sorry, Ilay.
Should I ping at channel for everyone to come?
Yeah, I think that's okay.
Time zone difference, so hard.
Yeah, I would have this is today's Halloween here in US, right? So I have to take my kids. Otherwise, that was okay.
Oh yeah. I'll be back in just 1 second.
Mm-hmm. How are things for you, Dinesh, back in India?
Sorry, Samarth, I missed your question. My internet was unstable.
How are things for you in India?
Regarding?
I mean, it's festive season, right?
Oh yeah. It's Diwali season. I today went out. Yeah. So it's really light up. Like nobody really remembers that it was COVID a few months back.
Okay, that's good.
It's really.
Hey, Jamie.
Good afternoon. How's everyone doing?
Okay, how about you?
Yeah, just fine, thanks. I mean, obviously, I don't know if it's the case for anyone else, but my workload's definitely ramping up in the last several weeks. It's been kind of a mess.
Yes, I feel that as well. Let's wait a couple more minutes.
Just a heads up, because you're not recording, I have not prepared much. So
We're definitely recording right now.
Okay, we are.
Sorry. It's in the top, it should be in the top left if you didn't know.
okay. Oh, that's fine. It doesn't matter. I'm just I'm not prepared much.
This is a freestyle meeting. I made a YouTube channel, but I don't know, like, I still haven't figured out, like, do we want to publish it? Do we not want to publish it? I don't know.
Has anyone specifically asked that you not, like as an attendee or presenter?
No one has objected. I just don't, I don't know, like, I'm indifferent, but I guess I'll publish this one unless Samar will tell me not to.
No, that's perfectly. I'm perfectly fine.
Okay, then.
Anyways, these are terrible, not so polished videos. These are like free flowing, so I don't know, but no harm in publishing. That's fine.
Huh, okay, I think yeah, today maybe Halloween and maybe time zone complications, so not many people, but we can start if you want.
Okay, so let's get started. Oh, can you enable the screen sharing?
Okay, serious question to everyone. Does anyone know how can I permanently enable this? I couldn't find this in settings. I'll do this right now, but like I have to change this every single time. And,
I think it's there in meeting settings, if I remember correctly last time.
Can you try sharing once again? Should work now. Hi, Raj.
Hello. Sorry, mixed up time zones.
No worries. Okay, so let's get started. So thank you everyone for your time today. So Today we'll discuss this one survey paper, I would say, very good survey paper that I found regarding the topic that I am considering for my literature review. So it's about neural question answering and specifically the task of machine reading comprehension. So in this paper, in this survey rather, what we are going to see is what are the different techniques, different data sets, and problem statements. So everything revolving around this big topic of machine reading comprehension. So let's start with the introduction. So as you can see in the highlighted text, is that the machine reading comprehension task is primarily introduced to test the degree to which a machine can understand languages by asking questions. So the whole idea about reading comprehension is that we humans, we say that we are able to comprehend or understand a passage or a text if we are able to answer any questions related to that text after reading it. So similar kind of task is defined for computers, and they say that if the computers are able to answer questions given a paragraph or a piece of text, then it clearly shows that they are able to understand the elements in the text rather than just doing a pattern matching. So that's what this machine reading comprehension task is all about. Some of the uses or applications is, let's say, in a search engine. For example, here in this picture, you see in the search engine, typically you imagine if you put in a query or a question, then you get a rank list of related links, right? Related web pages. But what MRC is trying to do is it is trying to give you the exact answer to that question. So rather than giving the rank list of web pages. So as you can see, how long is the longest river in the world? That's the question. And the answer which is coming out is 6,695 kilometers. And also where in the text the machine was able to find this answer. So evidence related to that answer. Okay. So that's a pretty powerful and difficult task as such, because we are not talking about like small passages. It's about long, bigger text and literally understanding the text. So historically,
So, Samat,
yeah.
Just one quick question. Like, we are evaluating model on the basis of their understanding of the text and like if they answer the questions. So who is forming those questions?
Very good question. And that's one of the topics in this paper, as in how do you formulate the data set? And you'll see what are the different types of questions. So this MRC bigger task will be broken down into different smaller subtasks. And there have been data sets created to address these questions and answers.
So in general, like I was like thinking, I was reading about it somewhere, like if we go about like understanding, so like machine is trying to understand something and we are validating it. So in the production, how do we validate that? Like, for example, there's a text that machine wants to, let's say, run algorithm on, and we as a user don't know it. So in that case also, how do we know that the answer generated by the machine is right or not? Is that also covered in the paper?
So what is covered is different types of tasks. What you are saying is, post you have built a model, let's say an MRC system, and you are querying the system, right? So while you are building what the paper covers is while you are building the system, what are the different components you need to take care of? How do you build the data set, training data set? How do you build the evaluation metrics? All those things. But once that is done and the model is in production, it's primarily, so what in industry, what at least from what I know is they do compute this online metric to improve the model and get the feedback. So if I don't know if you're able to see this small text here which
Thumbs
says
up. Yeah.
is the answer helpful or not. So that's the feedback loop which you get from the users of the system once the model is in production. So pre-production phase, development phase, you have your data sets, you have your evaluation metrics, and you rate your model according to that. Post, for a continuous improvement, you rely on these feedback mechanisms to further improve your model.
Yeah, because like this is a very classical example of, I think, self-supervised. I think where we would be needing self-supervised if we go ahead in future. So I was just thinking like it somewhere mentioned like some signal from the data.
Yeah. So this is a very, so these online metrics are pretty common in building these, what I call the search-based systems. It's not just MRC. Even if you go to regular search, how much time you have spent on your click-throughs, all those signals come back as a user, and those are used to either modify or enhance your queries, questions, and there are many things which are done with those feedback signals that come to further improve your the results.
Yeah, but the problem with these systems is like it's not translatable to training time. Like if we learn anything, we don't learn any improvement in our training mechanism. So we need to, invest more research on training time separately. So so that's why. Okay, let's see if this paper discusses a little bit where I'm.
Yeah, so I think that's part of the design of a bigger system, I would say. This paper doesn't cover that part. It only discusses about what kind of architecture you can implement, what kind of problems you'll face while building this system.
Sure.
Okay, so coming to the problems, historical problems. So primarily what people have tried in research is building some rule-based systems or some machine learning-based systems, very specific problems set like what, when type questions. But all those, let's say, methods were not very well performing. So because of some limitations. So firstly, the limitation is that all these older systems were based on handcrafted rules or features, right? So they needed a substantial human effort. So what it means is especially in this question answering space, there is not much data set. The quality of data set is improving on a day-by-day basis, but essentially or historically, there was not very good data set. And creating that kind of a data set itself was a big challenge. So this first point was very limiting. Second, these systems, the old historical systems, were not able to generalize very well on let's say, large scale data sets. So that was another problem. And also, like pre-deep learning, they didn't have any kind of contextual information. So those long range dependencies, they were not able to capture. So, but a lot of this changed. And as a result, if you see, there are new sets of data sets, there are new models coming in. So what this paper has done is it has divided this entire task into multiple facets. And the first is, let's say, looking at the machine MRC task in terms of smaller categories. So when I say smaller categories, it's like, let's say one kind of machine reading and MRC task could be a multiple choice question task. So what does that mean? It means that you are given a passage and you're given, let's say, multiple choice answers. And then now the task of the model is to pick the right answer from those choices. So that's one kind of task. It's called multiple choice task. Then there are this other scenario called closed tests, span extraction, free answering. So we'll go into more detail on each of these subcategories of MRC tasks, but essentially one dimension to understand this entire space is, first you need to understand what are the different task types that can exist in the problem space. Then the next element or next dimension is, suppose you have decided on the task type or task category, what is the general architecture? How would you build these MRC system in general? What are the basic components of build these systems? So which includes, for example, embeddings, feature extraction, context question interaction, concept prediction. These are the four main build basic components. So how you build these components? What are your options or choices? Then the biggest, say, hurdle is, how would you even create a representative data set, and what will be the kind of metrics that you are going to use? Because different question types may require different kind of metrics. And finally, this guy talks about some future trends, like, so traditionally it's like you will be just given one small passage and all these tasks are just tied to that one passage. But what they call as open domain question answering is like web scale. So you just have like whole of Wikipedia or whole of this thing, let's say web, and then you ask a question and you get an answer. So that's called, in the web scale is called open domain, but in between small one passage and web scale is something called a multi-passage MRC. So how can you handle with multiple passage and multiple documents and then move ahead? So those are some of the trends and some of the challenges in this space. So in summary, if you look at this picture, that gives you the whole, on a very high level, the problem space. So what is the problem? What are the different types of or categories of problems there in machine reading comprehension? What are the different methods or architecture that you use to implement this task? What are the data sets and evaluation metrics you use? And what are the different trends? What are future, let's say, challenges or areas of research? So any questions still here? I think this is a roadmap in a way. If you see, this will be a roadmap. We'll talk about first category of different tasks. We'll understand what are these. Then we'll go into the architecture in more detail. Probably, if time permits, we'll go into evaluation and new trends. Otherwise, we'll primarily focus this attention to these two aspects. Questions? No? Okay. So now let's focus on this. This is one of the first steps. So like I was saying, so machine reading comprehension is a textual based question answer. Now we are getting more specific. So it is more of a textual based question answering. So in general, question answering can be anything. You give me an image and you can ask a question for that image. That's a question and I get an answer. So that's a, let's say, image based question answering or knowledge based question answering. So this guy, when we say machine reading comprehension, it's only related to textual questions. So that's very important. And in this setup, what you get is you get a question, and the question is coming from a related context. So when we say related context here, you think of a passage. Imagine you're reading comprehension days or exams that you used to do. So when they say related context here, it is about the passage. So you are given a question, you are given a passage, you are given a question, and then you have to infer the answer to that question. And like I said here, the objective is to extract the correct answer, or sometimes even generate more complex answers. I mean, generate answers, not just like pick a kind of answer like multiple choice, but maybe you have to write the answer.
Quick question.
Yeah.
Do these MRC models, do they normally have some underlying language model, or are
We'll
they?
see that. We'll see that. That's in the architecture piece.
Because it would, just intuitively sound very crazy to me to, I wouldn't try to teach a kid to answer the questions without learning how to read first, I guess. Okay.
Yeah, so you'll see that this embedding, how are you going to generate those embeddings? Those are going to come primarily from your language model. And then how you use those embeddings and combine them. So we'll get to that. We'll see that topic when we are looking at the general architecture and the components of the architecture. So it will come in the embedding section. Okay, so more formally, the task is given the context C, question Q. The task is that you need to learn a function that takes these two texts as input and predicts the answer. Very simple on a high level. Now, like I said, sorry, I didn't touch it. So this machine reading MRC task is divided into 4 categories on a high level based on Genethal's thesis. So what they call the 4 categories are closed tests, multiple choice, span extraction, and free answering. So these, you can imagine it like different kinds of questions that you can get when you are given a passage. So let's look at what are these different kind of questions. Or setup. So technically, this is the simplest form of text you can think of, or questions that you can think of. So what they say is, in closed tests, questions are generated by removing some words or entities from the passage. So let's say I give you a passage, which is, let's say, talking about the history of US presidents. And then I just remove one word from that or entity from that question, saying the first president of United States was and blank. So that's the kind of, it's a fill in the blank in very simple terms. You can think of it like a fill in the blank question. And the text of that question is primarily coming from the passage. And it's a rephrased question. It's not an exact copy, but some kind of a rephrased version of the question with a fill in the blank. So the setting is given the context C, from which a word or entity is removed. So you are given the passage, you remove one word or entity generally. And the task is, for this closed test, is for the model to fill in the blank with the right word or entity by learning this function. So as you can see, it's a C minus A. So you just remove one entity and fill in the blank. Okay. So an example for such kind of, you can think like here, you can see the example here. So this is one of the first and very influential data sets that was created for question answering. And as if you read the passage, essentially this is talking about some person, getting the lawsuit, taking away the lawsuit and hitting someone and blah, blah, blah. But then the question is reformulated as producer dash or X will not press charges against entity 212, his lawyer says. And if you see, Wednesday, after an internal investigation by internal broadcaster found that he had subjected producer blah to an uninvoked physical and verbal attack, and somewhere they say they are revoking the charges or they will not press them. And the answer is entity 193. So this is kind of the task. So the question is here. The passage is here, and you remove one of the entities, you rephrase the question targeted to that entity in some way, and then the task is to predict that entity. Make sense? Any questions on the closed test type?
Sounds good.
Okay. Okay, so this is what also they called entity prediction or word prediction. So here you just need to predict one word or one entity. That's the simplest of the tasks. You don't have to predict a passage, or let's say give a sequence as output. Then we take the other type of question type or task type is multiple choice. As I was saying, this is very familiar to all of us, right? Given the context C, the question, and a list of candidate answers, the multiple choice is to pick the correct answer A for that question. Okay, so very straightforward this one.
You kind of said that the closed task is the simplest one.
Yeah.
Wouldn't multiple choice in general be?
Yes, it will be harder because now you have to deal with a sequence. In terms of analyzing the answers, you need to look at a sequence. You need to understand the sequence in the answer choices.
You mean each answer is a sequence of words?
Yeah. It's like our multiple choice questions. So
right. Okay.
So we are getting, previously we are getting the passage and we had to just fill in the blank with one word or entity. Now we are given a passage and a list of answers, which is even a little more complex. Okay. And now you have to pick one of the answers, which is the correct answer.
Yeah, I guess what makes me feel like this is simpler is because the number of answers in my mind, the number of multiple choice answers would in general be smaller than the number of possible like named entities or something. Yeah, I don't know. I guess it depends.
Yeah, I mean, we can also look at that way if the number of entities and other things. But at the end of the day, the task of the model is to analyze a sequence versus just analyze one entity as output. So it has to do more work. That's how I interpret it.
I think to Ilya's point, multiple choice question can be a little bit difficult as well if they have ambiguous entities in the choice.
Yeah.
On page 6, there's some examples about what they mean by multiple choice, and that might be important because it does have like sentence fragments.
Yeah. Here's an example.
Are they only looking at multiple choice questions in terms of that? Like they're looking at the potential answers are always sentence fragments and not individual words?
So they are only looking at multiple choices and looking at each of. So essentially they'll pick, in very simple terms, they will learn. They need to learn about the question. They need to learn about the options and then do some kind of similarity with the context, question, and answers.
Sure, I would just imagine that if the multiple choice was set up similarly to the closed test example, I would imagine it'd be a different kind of difficulty because if it was set up like the closed test example, it would just be like N381, N212, N153, etc. So that would be individual words versus.
Yeah. So entity was just one mean, common thing, but this could be any word coming from the passage. Generally, it's entities they kind of try to get through, but technically it could be any word. You're right. I mean, let's say if it was constrained to just identifying entities or fill in the blanks with entities, then you have a fixed list of entity choices, and then you can pick based on, let's say, I mean, it kind of a classification thing wherein you just pick the highest probable entity. But that itself is also tough because you need to understand the context of the question and the entire passage context. As you can see, there are many entities, right, in this example as well. But here it's only about entities or words. But here you need, imagine like an n-gram thing, right? You need to look at fragments to see how much is which fragment is making more semantic sense and more closer to similarity. So that's probably what makes this task a little difficult. But good question, I think. Any other questions? I mean, okay. So if not, then we move to the next another kind of a question type, which they call as span extraction. So if you see, which says that although these both closed test and multiple can measure the machine's ability to understand, their limitations. So essentially, words or entities are not sufficient to answer questions. Instead, some complete sentences are required. So maybe in some questions, what is required is that the answer is not just a choice or a word, but maybe a sentence, a smaller span of the sentence, or a sequence in the sentence. So these two, the other previous two problems don't satisfy this constraint or requirement. So what span extraction does is it says that given the context, which consists of n tokens, right? So your context will have n tokens. And the question, the span task is extracting continuous sequence. So within that passage, the answer is a sequence of words from the context. So that's what the span extraction does. So example, if we go to span extraction, so if you see, this is a big text, right? Computational complexity theory, blah, blah, blah. And then the question is, by what mean attribute are computational problems classified using computational complexity theory? And it's a sequence. The answer is inherent difficulty, which is a sequence of, which is a subsequence from the passage. So now you have to really look at really understand this passage in more sequences or more in depth, I would say, to answer this kind of question. Where exactly, which part of the passage is having the answer. Okay, so this is span extraction, another question type. And then the last one is the toughest, which is like free answering. And as you can make it from the name, it's like you're given a question and now you write an answer. The answer is not limited to the context, what is given to you, but it can also come from outside. So it's like generating, in very simple terms, it's like sequence in our seek to seek models, it's like the sequence generation model which needs to be built. And the generations process can happen based on the context that you have seen, or sometimes even from outside context that you're going to. It's like you're writing the answers. Okay, so we can see the example here as well. Like this is a big context, right? Multiple contexts come into play, and now you have why did Rachel Carson write an obligation to endure, and writes this to believe that man tries to eliminate. So which is coming from this passage or this context. Okay. So any questions still here in 4 types of these question types that we have seen? Okay. So now the other interesting thing is, how do you compare these different tasks? So what are the, every question type is having its own characteristics. So how do you differentiate between one in a more systematic way? So what they say is, in terms, there are certain characteristics that are looked at into each of these question types. Or let's say tomorrow there is a 5th question type which is coming, right? So there are certain characteristics, and those characteristics are scored for each of those question types. So the characteristics are, the first one is construction. So what this says is whether it is easy. So the first thing is whether it is easy to construct data sets, right? So the very first thing, whether can you construct, how easy it is to get a data set for that kind of question. So that's one dimension. The second dimension is understanding. So essentially, how well the task can test machine's ability to understand. So it's more about whether the model is able to, or the system is able to understand better. How much is the power of the, let's say, technique that you use to understand, or even the task, how much level of understanding the task requires to get an answer. That's essentially the understanding dimension. Flexibility. So this is more on the data set setup side. This is more on the, let's say, understanding of the data set. That the model needs to put in effort to come up to the answer. So these are more on the questions and the context side. This is more on the what kind of flexibility in answers. So we saw word-based answers, we saw multiple choice, we saw some span, we saw free text, right? So flexibility is what essentially how flexible is the answer. And how do you do, then the next thing is how do you do evaluation of this system and what is the application? So if you see here in this like one diagram, what they have done is they have put in all the 4 task types that we have seen and measured it on different dimensions. So if you see closed tests, it's easy, higher on construction and evaluation, but very low on, minimum on the application and understanding and flexibility dimension. Whereas multiple choice, now the difficulty level of getting that kind of data set has increased. So the score has come down to 3. And the amount of understanding requires is more, and application is more, evaluation metric requirement. Flexibility wise, there's not much flexibility, so it's considered to be in that space. Span extraction is little harder, and even this free answering is, if you see, understanding and flexibility and application are super high in score. So any questions on this? Because this is like a summary of what I was saying in terms of complexity and the or the difficulty of the task. Okay. And here we have some explanation what I just said about all these dimensions and question types, why each dimension is getting this kind of score. So for example, the disadvantage, if you see, are constrained to the sequence of original context, which is not what happens in the real world. But So with this, now we have defined the different question types. Now let's look at the meat, right? How would you build such kind of a system? So deep learning methods were essentially very important, or are very important to do this, but let's quickly look at the general architecture. So if you look at the how would we implement, or what are the different components of building such kind of an MRC system? So we have what is called embeddings. So in this, what happens is we give context and question as input, and we get both their embeddings. So the embedding component is just required to generate the embeddings of the question, raw context and question. Then we have a feature extraction. The feature extraction, you can imagine, like once you got the representation, the embeddings of the text, then how do you build more complex representations out of those embeddings? And then once you got those features, or let's say features out of those embeddings, and then the next step, this is one of the interesting blocks, which is how now this, how would you interact question with context? How is the question and the context going to talk to each other to see which are the probable answers, or how would you see which part of the context are more relevant for the question? So this is handled by this context question interaction, and then finally answer prediction. Okay. So like this is exactly what is mean. Embeddings is you take inputs, feature extraction is aimed at extracting more contextual information. In question, context question interaction is essentially developing the correlation between the context and the question. And the techniques that are used here are primarily driven by attention. So that interaction I was talking about is primarily attention will be the key element of that interaction. And there is also called a concept called multiple hops. So what, and unidirectional and bidirectional. So in attention, whether you're doing unidirectional attention or bidirectional attention, and also like you're doing one hop or multiple hops. So we'll go into more detail about each of these, but on a high level, hops means it's like, let's say if I give you a passage and a question, but I give you this constraint that you will be given, you can read the passage only once. You cannot read multiple times to answer the question. So that's called single hop. And multiple hop is like, okay, I'll give you multiple chances to read the question again and again, and then you can answer the question. So it's like we humans do, right? When we get a passage and a question, it's not that in one shot we'll learn everything or we'll understand the passage. We read it multiple times. So that's the difference between single hop and multiple hop. And then, of course, the last prediction is answer. So you can think of this guy as the very involved person. This one is the very most involved and most complex person. Okay. So now what we'll do is we'll look at different methods to implement or these different components. So, okay. And if you see, this is another very good picture. It says, okay, for these systems, these components, what are your choices? So for embeddings, you can go with conventional embeddings, contextual embeddings, multiple granularity-based embedding. So what these essentially means is you can use one hot. So conventional is like your what to wake, one hot, glove. Those are your conventional embeddings. Contextuals are more of your the latest ones like GPT based embeddings, bird based embeddings, Elmo-based embeddings. So this is to your initial question earlier. So these are your different kinds of language models you are playing with.
What are distributed embeddings?
So distributed embeddings are our word-to-vec glove.
Okay, let's word to that. Okay.
And contextuals are Bird, GPT, Elmo.
Okay, makes sense. And then the multiple.
Yeah, multiple granularity is what they say is these embeddings are maybe not very much, this representation of embedding might not be sufficient. So what you do is you tag along these, I would say, more language specific things like part of speech, named entity. We'll look at it, but you just tag along these these things along with these more denser embeddings.
Okay.
So that's called multiple granularities. That's why if you see, each of them have a plus. So they don't exist by themselves. They'll be tagged to either contextual or conventional.
Great.
And then we have this feature extraction. So essentially, so it's like you can think of it like a typical architecture. Take any architecture. You'll first have the words, you'll pass it through the embedding layer. So you get embeddings, right? And then you pass it through either an RNN, a CNN, or a transformer, right? So that's what they call as the feature layer, which is kind of transforming your space. And in the penultimate layer, you get a representation, vector representation, right? Which is a dense feature representation of your input. And then you use that for prediction purpose in the output layer. So that middle part between output layer and your input coming from after the embedding layer, that's called the feature extraction layer essentially. And it could be like you can see here, right? RNN, CNN transformers. And then within the contextual query interaction I was talking about, right? Unidirectional attention, bidirectional attention, one-hop, multi-hop. Those are how you interact with these features. And then answer prediction are essentially based on your question type, like word predictor, option selector, span, answer generator. So essentially your question types. Okay. So I'll not go in much detail here. It's pretty I explained it. But if you see like one hot encoding, and if you see, this is a very interesting table. It's kind of it gives you what kind of work has been done in different contexts by tweaking one or two dimensions. So if you read about any,
this is so much.
yeah. And if you see, then this is like 2019. Probably there's one piece which is not mentioned here, which is open domain question answering. So that's even a bigger task. Okay, so this, like I was saying, right, low dimensional vector representation, closely related words, then contextual thing is coming. Curve is again contextual and Elmo, GPT, we all know that, right? So I'm just running through this because I am assuming we all know about it. Any questions if you have, I can stop here. Anything in embeddings? I think we are comfortable, right?
So I think we didn't go over Elmo. I think last time we were going over BERT. We didn't go over Elmo. If there is any brief about it.
It would be good to go over. I don't know. That would be great if someone did that.
Yeah. I mean, so if you see, so we can talk in here. They give it in very small summary. So it's like to get these embeddings, you pre-train a bidirectional language model with large corpus. And Elmo breaks the constraint of limited parallel corpus and obtain richer word representation by collapsing output of. I have to read it, honestly. I have not read about Elmo in detail. So, but the idea is this is some kind of a contextual embedding.
That's fine.
Okay, so then Bert is here. So, okay, so first part of that picture, that big picture, we covered the embeddings, right? Embeddings and all these three types of embed. What does this mean? Conventional, contextual, multiple, granularity. We are here. Yeah, multiple granularity, as I said already. You can syntactic and linguistic information. You can encode that, enrich your what to wear or glove vectors with that information. And there's also in this case, what are different techniques? It's like character embedding. So instead of word-based embedding, you can have character-based embeddings or part of speech tags, named entity. This was an interesting technique I found, or at least I learned here, is you check the feature is exact match. What it says is whether the words in the question are they present in the passage. It's a binary feature. All the words in the question, or which ones are there in the passage as well. So exactly, it's a binary thing. So it says, let's say, who was the first president of USA, and the passage is talking about all the presidents. Then you'll find that, oh, president is there, first is there, USA is there. So all those features will become 111. Because the words in the question are also present in the context.
So this is for like feature representation of the question.
This is, yes. When you are, so your embedding layer of your, or embedding, when you generate the embeddings for your question and the answers, right? So for questions, you can tag this with this information.
Yeah.
Then query category is also a very interesting subcomponent you can think of, whether, so which essentially says that whether the question you are, what kind of category it is. Is it a what, where, who, when, why kind of question? That's another interesting feature that you can, or information that you can add. Okay, so in the interest of time, I'll just quickly run through feature extraction. So we know RNNs, right? So essentially this is just RNN showing here. So if you see, you have the question, you encode your question like the typical bidirectional RNN. You pass in words, you get the hidden states, concatenate them, and you get your these questions, right? Let's see, there's a yeah, they are slow. Okay, so this is the question kind of. So at the end of this, you get all your word level encoding of your, or features for your question, right? This is your question vector from a word level perspective. But we also learned this attention thing, right? So you can apply attention and come up, or some other technique, like you can do a max pool. So out of this, each of these, you can do a max, pick a maximum value and come up with somewhat a question representation. It's a question vector that you get out of these things. Okay. So this is called sentence level encoding, because now you are representing your entire question or context with just one vector instead of these multiple vectors. So that's an RNN based thing. Then there is this CNN. We talked about it in the understanding session that we had, right? So again, you have this question and you get this question vector by passing through filters and multiple layers. One major shortcoming, I think, the shortcoming from here for this guy was very slow and not very long sequences it can handle. It can handle, but not very long interactions. And this guy is very good in handling local information, but not able to handle long sequences. So that's where our friend transformer comes in. We know that. And yeah, it goes away, it takes those things out. So this quickly completes our feature extraction layer or component of the entire system architecture. Any questions on the feature side? Okay. So then now let's quickly look at the most complicated one and interesting one, I would say, for context question interaction. So the first thing that comes here is called the unidirectional attention. So here it's the classical setup. So we have our question vector, right? So based on that feature extraction step, let's say we got our question vector out, right? And similarly, we have our, let's say, passage text, right? And for each passage text, we have, for the passage, for each word, we can have these embedding vectors, right? For each of the words, right? So when we are passing our context or passage through the embedding layer, for every word in that passage, we'll have a vector, right? So what we do is we apply attention, use attention to from question to passage. So essentially we are taking the question vector and we are doing a attention. We are saying, okay, which of the word vectors within the passage should I pay attention to for my answer? So if you see after that, you get this distribution, right? Attention score distribution. And what this is telling you, okay, for this question, maybe this corporation is high, company is high, law is high. So that way you'll come to know which of the words in the passage are more important for your question. And this is a unidirectional attention because the attention you're doing this, you're paying attention only from one direction, from question to context. Okay. So you're getting question as input and you're looking at every word. So context is not looking at question. It's only question looking at context or to find out what are the important words. Okay.
Just one quick question.
Yeah.
So I was a little confused, like when we were discussing about sentence level embeddings for RNN, it was pretty clear, but for transformers, like, are we going to have sentence level embeddings or are we going to have sentence level WKQ or something?
At the end of the day, there's a vector which comes out of transformer, right?
I mean, each head, each transformer unit.
At the end of the day, you get one vector out, right? So whatever input you give, it goes through the transformer architecture, and the output is a vector or a list of vectors that you can then combine in whatever fashion you want.
I mean, like questions can be of different length and all that stuff.
Yeah, it doesn't matter, right? It's the same quality of a text, right?
So, I mean, let's say if we have, let's say we are encoding the question right now. So we're going to have maybe segment length of 4. Okay, I see. Yeah, I see how it's going on. Cool.
Okay. So at the end of the day, the feature, just imagine it like a black box, you get a vector out of it. How you get a vector out of it, that depends on the internal architecture.
Yeah, exactly.
So this is the corporation, and then you got the idea, right? Unidirectional. So here only the question is giving attention or paying attention to the text or the passage. The passage has no idea about question. So that's why this is called unidirectional. Bidirectional, if you look, what they say is both the guys interact with each other. So the context has a view. So if I look it from a context, this direction, So context is paying attention to question. So you get this kind of a vector here, attention vector here. And if you look at from this side, question is paying attention to context. And you get attention vector here from that perspective. So both guys are now looking at each other. So that's why it's called bidirectional. And then what you do is you come up with, you combine these two with different strategies. One is like you simply just concatenate everything together. So at the end of the day, when you pass it through the attention layer, this guy, let's say on this side, you get an attention vector for the passage, right? And this side, if you go, you get an attention vector from a question, this perspective. So the simplest representation is you can concatenate them together. You get one vector for the downstream task. Or you can use these two vectors in different, combine it in different mechanisms. But at the end of the day, you see how question and passage are interacting with each other. How you're learning the interactions or the alignments in a way.
So what's the reason for context to have a look at the question? Like context is not changing, right? Yeah.
Sorry? What?
No, go ahead. So my question is like, question needs to look at the context to answer, but why context needs to look at the question?
So it may
What's
be that
the reason?
You want to know there is some information, like there could be some sequences here, right? So some words, let's remember the word predictor entity thing. So if the question is only looking at those things, probably for entity kind of tasks, for closed test kind of tasks, this only one unidirectional is sufficient. But maybe for span detection kind of task, you may have to look both directions, or only this direction is sufficient. So depending upon the task, it may be required that you need to know both sides. Okay. So, we are already 3 minutes up. So I don't know. There is, I think, not much left, but is it okay? Just a couple of more minutes. So I'll quickly finish this and then maybe 5 minutes of questions. So one hop interaction I showed you, right? I told you, right? You look at one time and multiple times. So there are different ways to do it. Multi-hop is the same thing. And how they do it in multi-hop is that the method calculates between context and question on previous representations. And I would say, so here what they make use of, what the most interesting piece in multi-hop interaction is the use of memory networks. So every time, so what they say is some kind of, you reserve some kind of memory. So, and every iteration that you go through, you kind of update your memory vectors with those iterations. So the more you read, the more your memory networks or memory vectors are updated. And then you can, when answering the question, you can go to those memory vectors and see what's the best answer. So the key idea in multi-hop interaction to make it work is to use some kind of memory network. And this is, I think Weston et al. Has this old memory network paper, which is very influential for this kind of task. Okay. Yeah. So this completes the interaction, context, question interaction piece. And there are various architectures to do it. I mean, they have given multiple papers here. I mean, I cannot just references, and it's interesting. So if somebody wants, they can have a look at it. Now comes the answer prediction. So it's as we know, answer prediction is very task specific. So depending upon what you do, which type of question you are. So word predictor, option selector. So apparently here the unidirectional attention is very suitable. Question-based unidirectional thing. In option selector, CNNs are very good because what they do is, like if you have a where kind of question, those are spatial kind of questions. And CNNs are looking at very local piece of information. So CNN-based architectures are very popular here for option selector. Span extractor, I would say there are some kind of, so span means this is a more challenging thing because you need a continuous sequence of text from your passage. So what some of the methods or techniques that have been involved is called to build a sequence model and a boundary model. So sequence model, what it will do is it will output the sequence of positions where answer tokens appear to be in the context. So what it will do is it will look for where in the passage are the probable answer tokens, but they could be out of sync, right? Out of sequence. So to curb that, there's another model called boundary model, which kind of tries to curb it and bring it under one probable consecutive sequence. Answers obtained in such manner treated sequence for input context, which might, yeah, that's what I said. Let's say span, and the boundary model can handle the problem. Yes. And finally, the answer generator, wherein you use more like a seek to seek kind of a setup. So yeah, some additional tricks, what they say, you can do reinforcement learning, you can use rankers. So instead of just predicting one answer, you can have a bunch of probable answers and then you can rank them to get the best answer out of it. Sentence selector is also one very good technique. So instead of looking at the entire passage as one vector, you chop it down into sentences and then generate, as a first step, you first filter down it to the list of sentences which are more probable for your answer. And then from those sentences, you pick the answer. So it's a two-stage thing. You first build a sentence selector wherein you kind of chop your passage into sentences and pick the ones which are important, and then feed those important ones into the system and get the answer. So it's like localized, filtered search. You look at one part and look at the second part. Yeah, and that's it. I think we'll stop here. I think this is a good point to stop. So any questions before we close?
No questions from me. When you said knowing what most probable words are, that doesn't guarantee that you have like a coherent sequence, because they might be out of word. I thought that sounded like a dynamic programming problem.
Yeah. So it's, if you see here, that's what these two, that's how they are kind of in this paper proposed, right? You build a sequence model and a boundary model. The sequence model will give you all probable words which are there, or subsequences which are there, but then the boundary model will take them and kind of combine them either, or draw boundaries, saying, okay, out of all these, this is a very coherent one. And honestly, I have not seen this paper, so I can't comment how exactly they have implemented it. But on a high level, the idea that I can get is this.
This is great. Thank you.
Okay then. Thanks a lot, everyone, for your time. And
thank you, Samarth.
Hopefully this was helpful.
All right.
Okay then. Talk to you guys next week.
Yeah.
Bye.
See you all later.
Yeah, thank you.